Can artificial intelligence help discover cause and effect in finance? Every investor has heard that correlation is not causation. Today we'll see why that old warning decides whether a strategy makes money, and how a global competition tested the limits of AI models. Start with the difference itself. Two variables are merely associated when the distribution of one varies across observed values of the other. That's an observational, symmetric statement about their joint distribution. Causation is a more demanding claim. We say X has a causal effect on Y when actively setting X to a value, rather than merely observing it, changes Y's distribution. The do operator is simply a way of representing that intervention. Accordingly, causal claims are interventional, directional statements about the data-generating process. Think of a hot day. It drives both ice cream sales and drownings, so the two move together, yet neither causes the other. On this account, banning ice cream would not prevent drownings. To reason about cause and effect, we draw a directed acyclic graph, or DAG. Nodes are variables, and arrows are direct causes. Given a cause X and an effect Y, three variable roles matter most. A confounder is a common cause of X and Y. A collider is a common effect of X and Y. And a mediator sits on the path between X and Y. The DAG helps us choose a valid adjustment set, which we denote by S. To estimate the total effect, we generally adjust for confounders, but not for colliders or mediators. Get that wrong, and a non-causal path may remain open, a new one may open, or part of the causal effect may be blocked, biasing the estimate. Here is how badly it can go. A drug is tested on two kinds of patients, mild cases and severe cases. Within each group, a higher dose is clearly associated with better recovery. But the sickest patients get the largest doses and recover the least, so pooling everyone flips the trend. Now higher doses look harmful. This is Simpson's paradox. Statistics alone cannot tell us which trend is causal. Here, the graph tells us that severity confounds dose and recovery. Under that assumption, adjusting for severity reveals the correct treatment effect. Now, why does this matter for investing? A factor model writes returns as exposures times factors. To build a portfolio, we minimize risk subject to target factor exposures, and the optimal weights depend directly on that exposure matrix. So here's the trap. A model can forecast returns beautifully, yet if its causal structure is wrong, say it controls for a collider, the attribution of returns to risk factors is wrong, and the portfolio hedges the wrong risks. Even with perfect means and covariances, the weights can flip sign. You buy what you should have sold. That's why there is no efficient capital allocation without a causal factor model. Where does the causal graph come from? It can be informed by theory, experimentation, and causal discovery algorithms that find graphs compatible with the data. Let's focus on those algorithms. There are four main families of causal discovery algorithms. Constraint-based methods, like PC and FCI, test for conditional independence. Score-based methods, like greedy equivalence search, optimize how well a graph fits. Functional methods, like LeNGAM, exploit asymmetries in the noise. And supervised, machine learning methods learn the patterns directly from many datasets whose true graphs are already known. That last idea powered the ADIA Lab Causal Discovery Challenge of 2024, proposed by Guido Imbens, Marcos López de Prado, and Miguel Hernán, and hosted on CrunchDAO. The task: for a treatment X and outcome Y, classify every other variable into one of 8 causal roles, from confounder and collider to cause and consequence. Competitors worked with roughly 47,000 synthetic datasets, including about 25,000 labeled training datasets with the true graphs revealed. Solutions were scored by multi-class balanced accuracy, where random guessing gets just 12.5%, and the prize pool reached $100,000. The response was global. 1,904 researchers registered, and together they sent in 3,343 solution attempts. The competition ran from August to October of 2024, with an award ceremony that November, drawing active participants from the United States, India, China, and across Western Europe. What did they build? Some leaned on classical, constraint, and score-based discovery. Many more turned it into supervised learning with rich feature engineering. Others reached for deep learning, from transformers to amortized models like AVICI. But the strongest entries were hybrids, combining a supervised core with causal features and ensembling, and that blend proved the most robust. And the results were striking. ADIA Lab's baseline scored about 40% balanced accuracy. Yet even the 10th place team reached 66, and the top 3 all cleared 74. The winning solution, a graph neural network approach using edge features, hit 76.7%. Hierarchical graphs proved easiest to read, while preferential attachment graphs were the hardest for everyone. Let's pull the threads together. Association is not causation. The causal graph, not p-values or r-squares or similar scores, decides the correct controls. Avoid risk models that are not supported by a causal theory. A causally misspecified risk model can turn good forecasts into wrong allocations and systematic losses. Causal discovery gives us tools to find graphs consistent with the observations, helping researchers narrow their search. And the ADIA Lab Challenge showed that, given the right setup, AI is a viable tool for causal discovery. If you want to go deeper and learn how machine learning and causal inference are bringing rigor to quantitative finance, visit www.quantresearch.org.